So what I'm going to do over the next 50 minutes or so is talk to you about the work ongoing in my group. I know that we're running a little bit late, so if I can sort of reclaim some of that time for you, I'll do my best. So as Yatish mentioned, my background's in computer architecture and system software. And so I'm going to be talking to you about those topics in the context of the design of neural interfaces. Now, I know that there was another really great keynote earlier this morning on neural interfaces, and I'm sure that there was a lot of motivation for the field. So what I'm going to try and do in this talk is perhaps motivate the work from a slightly different angle, that is through the lens of the computer sciences and the history of computer science. And then I'll deep dive into what we've been doing in my group. Um, I should also say actually that uh, out there in the audience are two of my mentees, my postdoc Raghavendra Potukuchi and my PhD student Mohammed. So they should be there amongst you. So if you have questions, please feel free to talk to them about the work that we're doing. We are looking to expand our group, so we're looking to hire PhD students and postdocs. And if you're interested in what I'm about to present, please find them to talk to them about the work. Okay. So let me begin with why neural interfaces are more connected to the computer sciences than maybe we sometimes appreciate. So if we go back in, a little bit historically, in 1945, there was this extremely influential paper published in the article published in the Atlantic magazine by a person by the name of Vannevar Bush. So Bush was sort of a pioneer in science and tech policy in the country. He spearheaded some of the work that laid the ground for the Manhattan Project and the National Science Foundation. And this article that he wrote about this thing that he called the MEMX. And the idea behind the MEMX was that it was this electromechanical system that would essentially act as a supplement to human memory. So the idea would be, and this is a diagram of the MEMX in his article. So the idea was that human beings would be able to kind of upload and seamlessly download all of their electronic or written records from a machine like this, and it would effectively give them infinite capacity to remember all of the experiences that they had had through their lifetime. Now, obviously, this is, was a hypothetical machine. You can't build something like this, but it's actually proven to be very influential in the computer sciences. Early hypertext systems, the World Wide Web, knowledge-based software, and so on, you could sort of argue, trace their beginnings to the idea of the MEMX. And what's interesting is that actually, in parallel to all that work, which we associate with the computer sciences, there was also this other vector of work that got spawned off, which basically said, well, if we could build something like the MEMX, how would we be able to interface it with the brain? And if we could interface it directly with the brain, could we sort of upload, download all our records, memories, skills, and so on? And could we sort of even use it to augment human cognition? And so the MEMX gave rise to this entire field called cybernetics, which the descendants of today are what we think of as artificial intelligence and, and robotics, among others. But there was also this entire emphasis on like direct interfacing with the brain at that time. And, that sort of creation of this tiny subfield led to some really interesting experiments in the 1960s. Here's one of them, which was conducted by Vivian Dovey and William Gray Walter. And they sort of pioneered what we now, some now think of as the first brain-computer interface. So they worked with patients who, who were had paralysis and sort of other tetraplegia and spinal cord deformity, and had lost basically the ability to move. And so what these people did is they worked with this patient to embed electrodes in the person's motor cortex. And they showed that just by sort of the person's thoughts, they could have that set of electrodes control the advancement of a slide projector at that time. And so this is the first example of using kind of direct brain signals to sort of actuate movement of some sort without the need for motor control with your body. And that's what we generally think of as the first PCI today. And since then, this entire field of brain-computer interfaces, it's come a really, really long way. It's used to advance the basic sciences. For example, in the last 10 years, several experiments have shown using brain-computer interfaces that you can electrically stimulate an area of the brain called the entorhinal cortex, which is sort of deeply wedged in. And I'm showing it to you and sort of highlighting it in this diagram. If you stimulate that part of the brain, you can arrest memory decline. And so, I mean, the thing to take away here is that it's really interesting how this sort of thought experiment of the MEMEX spawned off this field in conjunction with several other fields that we think of in the computer sciences. And where we are right now in this field is that there's a lot of interest in building more and more capable brain-computer interfaces to do two things. The first is continue advancing research in the brain sciences. This example that I showed you of the entorhinal cortex, the success there really, was dependent on the fact that brain-computer interfaces or BCIs are getting more and more computationally capable. The other very compelling use case of BCIs increasingly is that it looks like they can be used to treat very crippling neurological and neuropsychiatric disorders. So let's take some examples. The most sort of promising one where BCIs are seeing actually FDA approved use today is in treating pharmacologically resistant epilepsy. So there's 100 million people worldwide with epilepsy, and about 30% of them suffer from seizures that last tens of minutes to hours per day despite the use of pharmacological intervention. So within the US, the FDA actually approves the use of implantable devices surgically embedded under the skull, placed on brain tissue, where these brain-computer interfaces can kind of detect the advent of a seizure and then electrically stimulate the brain to mitigate symptoms of it. And there are several companies that sort of sell these implants today, Medtronic, Boston Scientific, NeuroPace, and so on. And that pool is expanding. But I think that's just sort of the tip of the iceberg. In clinical trials, there's been increasing evidence that these types of devices could be used to assist people with paralysis. So on the left is a very well-known sort of clinical trial conducted by a consortium called BrainGate. So this is an individual who's lost the ability to sort of move their body for the last, I think, 30 years. An implant was placed on her motor cortex. It picks up how the neural circuit activity corresponding to how she wants to move her hand, and control signals are then relayed to this robotic arm to sort of replace what the biological limb would have done. On the right is a similar kind of neural implant or BCI. It's embedded on the part of the motor cortex that detects how this person is trying to move his lips, tongue, jaw, and larynx. And from there, reconstruct what this person's trying to say. Now, this person's paralyzed and has lost the ability to speak. So, by inferring what they're trying to say, you can sort of emit text to a terminal and have some rudimentary form of communication. So, where the state of the art is in these kind of speech prosthetics today is something like 60 words per minute. We speak at about 160 words per minute conversationally. So we're far off, but it's a start. And that's the kind of start that we're seeing in a variety of different ways. So in the last decade in the popular press, there's been reports of using these devices to restore vision to people who are visually impaired, at least partly, treatment of neuropsychiatric disorders of many types. Now, of course, this is the popular press. You have to read this with a bit of grain with a grain of salt. But the fact of the matter is that there are many ongoing clinical trials, and it looks like these devices are going to potentially restore lost capabilities to individuals who need them in the upcoming decades. So really, I mean, to take a quick recap, I mean, what I've basically been sort of presenting to you is the state of the art for where these machines are going. And as much as there's this vision to try to heal, neurological disorders, there's also this promise of augmenting the healthy brain even. And so increasingly, people have started conducting studies about short and long-term memory. They've started showing that electrical stimulation of certain brain regions can improve memory recall even in people who don't have memory decline. And so the future of these devices may far transcend just the treatment of neurological disorders. So now, why do we care? We're a computer systems audience. Why is this related to us? Well, the way I think about it is that brain-computer interfaces present a new form of doing I/O with a computer system. And historically, whenever we've had new forms of I/O, we've actually made a lot of advances in the way we build our machines. A great example of this is Sketchpad. Sketchpad was pioneered by Ivan Sutherland in 1963. It was the first medium that allowed humans and machines to converse via the medium of line drawings and create sort of objects out of them. And it was Now that, it was a highly influential system. I mean, today, many of the things that we think about with object-oriented programming, computer graphics, HCI, I mean, it was born from Sketchpad. But the fact is that Sketchpad would not have been possible to sort of achieve and develop without innovations in machines that made it possible to kind of render fast enough, have adequate response time to Sketchpad's needs. And the machine that I'm talking about is the TX2 machine, which was built at MIT at that time. And in order to achieve the kind of performance requirements that were necessary for Sketchpad to run, the TX2 pioneered a whole host of systems innovations. So, using transistors instead of vacuum tubes. This was one of the first machines that had a form of paging between a memory and sort of a persistent storage, time sharing. There were all kinds of interesting instruction set architectures proposed to enable the functionality of something like Sketchpad. Compilers were built to sort of transform the lines into 3D shapes, and so on. And the TX2 ended up becoming so influential itself that it became the basis of the formation of Digital Equipment Corporation, actually. And DEC is the ancestor for practically all the work that's going to be discussed at ASPLOS in the next few days. So this has been a highly influential kind of machine for systems design. And it's just a way of showing how much I/O can drive how systems are built. And so the way that I like to think about it is that if Sketchpad required innovations in systems design that came about with the DX2, it's really interesting to think about what systems designs will become a necessity to interface with the human brain. And that's where we come in. And this is an area I've been working on for, I think, at least 8 years at this point, starting with my post-tenure sabbatical. So in my post-tenure sabbatical, I learned to do animal work with brain interfaces. This is a video that I collected by essentially interfacing with the hindbrain of mice. This is a region called the cerebellum. It's very deeply kind of wedged in the brain. And using instruments like this gave me an idea of kind of the systems challenges that we have to surmount to have BCIs deliver on their true potential. So I'm going to walk you through what those systems challenges are now. Before I deep dive into that, though, it's worth kind of taking a step back and just sort of laying out the space of BCIs a bit better. Brain-computer interfaces, as I've been describing them, I've made it sound like they have to be surgically embedded under the skull and placed on brain tissue. That's obviously not the case. You can have wearable BCIs that pick up signals over muscle fiber or the skull via helmets or something like that. But the problem with those instruments is that your muscles and your skull, they end up attenuating the brain signals that emerge. And so if you really want high fidelity signals, today, most often neuroscientists use these implanted electrodes, although technologies like optical ones may change that in the future. But implantable BCIs are what most state-of-the-art clinical and research kind of deployments focus on today. And with that, you embed these things called intracortical microelectrodes on the cortical surface and read from brain activity there. Now, implantation gives you high fidelity signals, but it also presents some really big problems. The first one is that brain tissue is very sensitive to heat. So if you're implanting a foreign agent in the brain, you better make sure that that doesn't overheat the brain excessively. The clinicians that we work with basically say that if the brain tissue exceeds over about a degree Celsius in temperature fluctuation, you risk damaging the cellular structure of it. And so practically, even though temperature and power have very sort of non-linear and interesting relationships, and practically federal agencies that kind of govern this field suggest that the implants themselves and anything on them not exceed about 15 milliwatts of power, or more generally, tens of milliwatts of power is what you have to play with. Now, that's a problem if you consider the fact that you're trying to read huge amounts of data off the brain. You may not need to read the data of all of the neurons in the brain, but we do need to read an adequate amount in order to do useful things with it. And there's about 86 billion neurons in the brain. If you sort of do a back of the envelope calculation using the sampling rates and resolutions that neuroscientists like to see, you'll see that reading all of the neural activity would require streaming data out at about terabits per second. And this is a huge amount of data. The only communication medium that funnels that much data today is the underwater cables that connect telecom infrastructure across continents. So this is obviously a really, really long-term goal, and hopefully we can do useful things before going there. But the problem today is that if you look at state-of-the-art BCIs, they fall woefully short. So they read only at about kilobits per second, tens of kilobits per second or so, without breaking through 15 milliwatts of power. There's ways to increase that interfacing rate, but it comes at the cost of some other things that I'm going to talk about shortly. The other thing I should point out is that, historically in this field, a lot of the emphasis was on technologies that would drive reading the data out. So building electrodes, for example, and that still remains a first-class problem. There's a lot of challenges in building electrodes. Scar tissue forms around electrodes that are embedded on brain tissue. So there's a lot of work that needs to be done there. But I think what's interesting from a systems perspective is that we are seeing adequate progress on that side, that we can start to think about what compute would look like if these electrodes get better and better. So in the last 6 years or so, in general, the number of neurons we can concurrently read from has been doubling every 2 years or so. Now, there's a bunch of caveats around this exponential growth, in terms of what do the electrodes look like, do you want to use optical technologies and so on. But the point I'm trying to make is that we are kind of on this exponential increase of data, and that means that there's interesting computational challenges to now look at. And so in my group, we've been thinking a lot about how can we process the data at a higher volume? How can we go beyond kilobits per second and go to at least tens of megabits per second in the hope of paving the path to eventually getting to gigabits per second and beyond? Now, so we've got this huge volume of data we want to read. We want to do it under 15 milliwatts. And that's already challenging. But what's going to make it even more challenging is that we want to decode this data at line rate. Line rate here means that we want to do this within milliseconds. And the reason for this is that a lot of the brain-computer interactions we care about require that kind of fast decoding. So if you take epilepsy, for example, you get about 10 milliseconds between detection of a seizure and electrical stimulation of the brain to mitigate symptoms of that seizure. If you go beyond tens of milliseconds, you might still be able to mitigate symptoms, but the effectiveness of doing so starts to drop off. And so you really want to do this kind of decoding at line rate if possible. Okay, so, what we've talked about is we have these tight power caps that we don't want to exceed. We have high data rates we want to kind of look at, and then we want to process at line rate. And so you might think that, well, the way to do this is to really, really specialize our hardware. And this is what the sort of state of the art in this field has basically been. But one of the things that I think is going to become important in this field is relaxing that specialization. Because as much as specialization buys you good performance per watt, you also want some flexibility in programming of your machine for a variety of reasons. The first is that the neural decoding algorithms that are used, many studies have shown that you need to personalize it to the individual. So overly rigid hardware that comes in the way of that is problematic. The second thing that people have seen is that, the electrodes we talk about, they form scar tissue around them. They can sort of drift and so on. And so periodically you need to correct the algorithms for things like that. And then finally, you have plasticity in the brain. So even, without those problems, these decoders need to be retrained almost daily in order for them to accurately pick up what the brain's intent is, or if there's, sort of some kind of disease in there. And so you don't want overly rigid hardware that comes in the way of all these things. The other big problem is that this is a nascent field still. And so there's a lot of emerging algorithms that are coming up in this space. In particular, the recent success of machine learning and neural network methods here is really picking up. And so there's lots of sort of activity in coming up with essentially new algorithmic decoders. And if an individual is going to go through the hassle of doing some form of surgery to embed these devices, I mean, you really want to be able to support more rapidly evolving algorithms than something that's overly fixed function. And finally, as a computer systems community, I think this is easier for us to appreciate than perhaps others. There's a real value to having a hardware target that is flexible enough that it can act as a stable hardware standard for many different software designers to build algorithms for. This allows you to sort of unlock software and hardware people from having to really be overly tied to one another. And it just promotes productivity in any kind of computational domain. And this is no different. And so that's why I think stabilizing the hardware target, which will require some flexibility in the hardware target, will become important going forward. The last thing that's also worth mentioning is that a lot of the brain-computer interfaces that have historically been built have allowed engagement or interfacing with one brain site. But there's increasingly accumulating evidence that most neuropsychiatric and neurological disorders arise because of network dysfunction amongst different brain sites and neural circuits on them. And so I think going forward, there's going to be a big emphasis on not just single site interfacing, but multi-site interfacing. And that's going to present interesting systems design problems as well. And here, I think I'm trying to show you an example of where multi-site interfacing might be helpful. You can imagine something like a seizure. What often happens is it originates in one brain region, but then it travels to the other. So if you can work out a map of where a seizure is likely to travel and electrically stimulate the target site, you are likely to have a more effective treatment option than just interfacing with one region. Okay, so this is the span of design goals that we have. And one way to think of everything I'm saying over here is that we're trying to build a flexible architecture that allows line rate processing of a data stream that's about 100K times higher than a 4K video. And that to under 15 milliwatts, even though the servers that stream your sort of Netflix videos do this at watts of power. So this is obviously a hard problem. Um, Over the next few minutes, I'm going to spend time talking to you a little bit about how we've been trying to address this problem in my group. Over the last few years, we've been building and taping out a chip that we call Halo that's used for single site BCI interfacing. And we've also been working on then extending Halo so that we can have multiple Halo chips interfacing with different brain sites to realize a more distributed brain-computer interface that we call Scalo. So let me walk you through those topics. Before I go further, though, it's worth mentioning, and I'm sure many of you thinking about it at this point, this domain brings up many security, privacy, ethics, and legal challenges. We're on the cusp of trying to figure those challenges out. I am not an expert in that area, but I'm really interested in it. If you're curious to know what we've learned so far about this field, please talk to my postdoc Raghav and my PhD student Mohammed. They'll be actually presenting some of our initial findings at the Hot Ethics workshop that I think is taking place tomorrow, if I'm not mistaken, in conjunction with ASPLUS. So please find them to talk about this a bit more. Okay, so let's start with Halo and what we've been up to there. And in order for me to help explain what Halo is and why it's built the way it is, it's useful to think more broadly about a generic neural decoding pipeline and what it looks like. Neural decoding pipelines basically take in brain signals and push them through three coarse-grained stages. There's one stage that's used to remove artifacts. So in brain signals, oftentimes noise gets injected if the individual with the implant does something like sneeze, for example, or moves their head in a kind of a jerky way. So those tend to be predictable artifacts that can be filtered out of the signals. Now, once that's done, there's usually some kind of feature generation stage that the signals get pushed through. And then once those features are generated, there's some kind of classification step that arises. So the kinds of things that we try to classify are like, well, what kind of neural activity corresponds to wiggling of the thumb on the right hand, that kind of thing. And based on the classification, some response is usually taken up. Now, algorithmically, what sits in those three big boxes is a really, really vast and rapidly growing array of signal processing and machine learning methods. Historically, it's been signal processing, more recently, machine learning methods. And this field has been, growing bigger and bigger here. Now, I don't expect that those algorithms will all be possible to embed on the implant itself. I don't even think it would be actually necessary to do so. What I anticipate will happen in this field going forward is that some amount of compute will support some portion of that algorithm on the device itself. And there'll be radios and other kind of communication medium that stream data out to an external system where other parts of the algorithm are handled. So for example, I don't know why you would ever really want to train maybe a neural network on the device, although there could be reasons. I would imagine the heavyweight training would happen on an external system, whereas maybe inference and model serving might happen on the implant itself. So that's what I think the world is going to look like. Now, in order for me to help explain how those algorithms fit in to the overall BCI, I also need to spend a little bit of time telling you what other components comprise one of these implants. So let's take an implant designed by Neuralink. So this is one of the companies that's been in the popular press a lot. It's working in this space. And if you look at a typical implant package, it's made up of a few key components. The first one is the sensors. There's many different sensor technologies and electrode technologies out there. I'm showing you here electrode technologies, although optical, magnetic. There's many other ways you might want to do this. Even in the electrode space, there's a lot of variety. We use for our work a lot of the time something called a Utah array, which is it's a more one of the more mature electrode technologies that's out there. This is sort of a millimeter squared grid of something like 100 probes that puncture the top 2 millimeters of the brain surface. But there's a whole lot of others things like grid electrodes, strip electrodes, increasingly a device called neuropixels, and so on. Now, the sensors that we work with, they stream data out at about 46 megabits per second. And for that kind of data rate, the sensors are not where most of the power is going. Certainly not for reading. If you're using the sensors to electrically stimulate the brain, then there's more power that's dissipated. But even so, this is not usually the dominant source of power dissipation. A bigger source of power dissipation is the analog electronics that are used to digitize the signals that the sensors pick up. For the data rates that we've been looking at, the ADCs on these kind of units, milliwatts is what they'll sort of dissipate. There's also radio links usually on these devices. Now, you could wire these devices, and oftentimes the early implant designs, that's what they did. They'd have a wire placed on the implant itself that would directly link up with what's called a pedestal that's placed on a receiver that's sort of placed over the skull. The problem with wires is that they pose surgical risk, and lots of infections arise from the use of wires that penetrate through all of the different layers of the skull and skin between the brain tissue and over the skull area. And that's why radio links are really where we want to go. But even with radio links, there's a lot of sort of, careful engineering that needs to be done. So here, for example, I'd shown you this speech prosthetic at the start of my talk. You'll see that there's this like pedestal placed on the skull of the person. So what's that doing there? Well, what that is a receiver for radio signals from the implant under the skull. And we place a receiver there because this radio was designed to be a short range radio in order to save power. And as you can see, even short range radios, they present this kind of tethering issue, which patients really complain about and we want to move away from. And so the radio links that we want to target, we really want to have sort of transmission ranges that go beyond the short range that I'm talking about. We don't build radios in my group, but I'm very interested to work with people who do. We've been doing a lot of our design, assuming off-the-shelf 200 picojoule per bit radios. There's a lot of other factors to sort of take care of in radio design, like the bit error rates, the dimensions of the radio, the transmission distances, and how they sort of influence like the size of antennas on these things. So happy to talk to people more offline about many of these trade-offs. But the radio link we use is 200 picojoules per bit with a transmission range of about 10 meters at 46 megabits per second. Now, what all of this means for us, and as the people building the microprocessor on the digital electronics side, is that we're left with about 12 milliwatts of power to play with. And so that's kind of as a consequence of all of the other components that we see over here. And so the Halo chip that we've been taping out, and here's some pictures of the tape out in 12 nanometer CMOS, it's rated to not exceed about 12 milliwatts of power dissipation. And the way we try and stay within our power budget is to support the algorithms that we care about using a collection of flexible ASICs. Okay, so I'm going to talk to you about what I mean by this. And the best way to sort of go through that material is to tell you a little bit more about the types of algorithms we've chosen to support as a first cut of our design. So there's four broad classes of algorithms that we've chosen to focus on. And we picked these four classes because we think they do a good job of sweeping through many of the methods in this space. They don't cover them comprehensively, but they've at least give us sort of a rough idea of the challenges of, what it would take to build more and more of these decoding algorithms. So let's start with compression. So we've got support for lossless compression in our Halo chip. The idea is pretty straightforward. If you can compress the data, then your radio needs to send less data out, which allows you to save energy from your radio side. The trick, of course, is you got to make sure that the compression itself doesn't dissipate so much power that you completely undo the benefits of lowered radio energy usage. Um, so we've studied a bunch of lossless compression algorithms to understand how they do on brain data. So using brain data collected by our collaborators, we've studied how well off-the-shelf compression algorithms fare on data collected on a monkey in the motor cortex of the brain, specifically in two regions, neural circuits corresponding to arm movement and leg movement. And here are the compression ratios that we've seen across the bat over here. Um, so what this should give you is roughly kind of an idea of what kind of compression headroom we have and how much the radio might be able to save energy using this. That's one big takeaway. The other thing that's kind of worth mentioning is that I've emphasized here lossless compression. And you might be wondering why, because why not lossy compression? I mean, the sensors themselves have loss, obviously, in what they're detecting. So it seems perhaps overly conservative to use lossless. I think that in the future, lossy compression is where this field will go. Right now, we've picked lossless compression because the brain isn't understood well enough yet for our collaborators to feel comfortable dropping any data. And so lossless compression is just sort of a pragmatic step that we took to try to improve the chances of the Halo chip being actually used by clinicians in real settings. But I think lossy is where we're going to go eventually. Overall, these compression numbers save about 1.4 times in terms of power, as I'm going to show you. But before I go there, I kind of want to pivot a little bit and talk about a second class of applications we also support that have to do with spike detection. Now, I just talked about how we want to do lossless compression. There is one exception to this, which is spike detection. The idea behind spike detection is that in some cases, we actually feel comfortable dropping the analog shape of the spike that we have and just create spike trains of essentially yes, no's, did the neural signal spike. And the use cases where these are found to be adequate are oftentimes in movement intent detection kind of algorithms in clinical use. So for people who are paralyzed, if you want to figure out how they're trying to move their limbs, what's been shown in the last 5 years or so is that just looking at spike trains might be good enough. And so we've got support to detect spikes using a couple of algorithms, nonlinear energy operators and discrete wavelet transforms. And since this is a form of lossy compression in a sense, you can think of this as giving you a compression ratio of about 30x or so. Okay, so the two other classes of algorithms that we support. One is movement intent detection, the other is seizure treatment. These are more clinical in nature. Let me tell you about movement intent. The specific form of movement intent that we support, there's two sort of variations. The first is we support spectral methods that allow people to detect when an individual has essential tremor. So this might be somebody with Parkinson's disease. You can figure out when the essential tremor is kicking in so that you can choose to electrically stimulate the brain at that point rather than always have ongoing stimulation, which dissipates way more power and energy. Okay, so this is a power savings technique. The other thing that we can decode is hand and finger movement. Again, we use spectral methods with a linear sort of kernel. The algorithm that we've supported is something that our collaborators have told us has a 95% decoding accuracy in the studies that they do. It allows you to sort of send control signals to a prosthetic that might be able to help do the hand and finger movement on the individual's behalf. So that's the movement intent side. Seizure treatment is something else that we support. The biggest group of our collaborators on the clinical side are actually epilepsy experts. So this is this is the set of decoding algorithms that I think we're more confident about than even the others. So the methods that we use are a combination of filtering and spectral sort of cross correlation measures. And the particular algorithm that we implement, we've been told by our clinical sort of collaborators here at Yale, is that on the patients that they implant devices in, these algorithms tend to catch about 90% of the seizures um, from their sort of rough analysis. Okay, so those are the four classes of algorithms that I'm going to talk about supporting. And Halo is designed to support these algorithms using 5 design principles that I'm showing you over here. Rather than going over them one by one, I think it's easier for me to show you how we built up our hardware using these, and then we can kind of revisit these design principles. So I'm going to compare how one might go about designing really power efficient hardware for something like those algorithms versus what we do. So on the left-hand side is what one might think of first doing and what we started by first doing, which is what I refer to as a monolithic ASIC approach. That is, look, I've got a compression algorithm I want to support, maybe LZ4. Let me build an accelerator that's customized to LZ4. Now you can do that, but what we found is that actually there are benefits to be had instead by looking more carefully at what LZ4 is doing computationally, understanding that it's made up of a Lempel-Ziv match stage and a separate linear integer coding stage, and building 2 separate ASICs for each one. Because if you do that, you can clock the LZ and LIC stages at much lower frequencies to meet the target data rate that we have of 46 megabits per second instead of the LZ4 monolithic ASIC. And so here we have a 5 times savings in power with this approach. If you want to kind of more conceptually understand what is it that we're doing here, we're basically saying that if you build a single accelerator for a computational task, the minimum frequency that you have to clock that entire accelerator and all of the hardware that's in it at is the one that needs to support the target data rate you have in mind. But if you actually look computationally at what sits inside these accelerators, there happen to usually be many different stages that are churning output to what comes downstream at different rates. And so you end up having to, with a single accelerator design or the monolithic ASIC, you end up having to overclock a lot of the hardware in ways that you wouldn't have to deal with if you created 2 separate accelerators instead. So that's the rationale for the design of our mini ASICs, or what we call processing elements on the right. Now, the other nice thing about designing these separate ASICs is that if you have other algorithms that use some of those ASICs, you can use up that hardware instead. So, for example, we also wanted to support LZMA as a different compression strategy. And now we can reuse that LZ block that we designed for the LZ4 compression case. All we have to do is to put a programmable switch, which is that circle with the cross that I'm showing you on the right-hand side. And that switch is used to govern the data flow between the different accelerator tiles. Now, looking computationally at what sits inside the MA stage, you'll realize that you can go a step further as well and break that down into a separate MA and range coding stage. And that'll allow you to clock each one at a much lower clock rate than the monolithic ASIC and allow you to save power again quite substantially. Now, one question you might be wondering about is how fine-grained do you want to get with this ASIC design? So there's this sort of trade-off. You want to get it fine-grained enough that you get power savings, but if you make it overly fine-grained, then you'll start dissipating more power on the communication that the sort of this programmable data flow network has to support. And so there's a balancing act over there that you need to kind of hit. Going forward, with other sort of compression strategies that we looked at using wavelet transforms, you can reuse the MA and RC processing elements. Spike detection, same story. You can reuse the discrete wavelet transform accelerator. For movement intent detection, we built again a bunch of ASICs, some of which could be recycled with seizure treatment decoding algorithms. And so this is the state of the PEs that we ultimately build. And you do need to leave the PEs somewhat programmable because, for example, the FFT has to be configured with a different number of points depending on whether you're doing movement intent decoding or seizure treatment. But that's easy to configure up without drastic changes in the hardware. So in a 28 nanometer CMOS physical synthesis sort of flow that we studied, these were the power and frequency numbers that we saw. You don't have to look at this busy slide in detail. Really, the main takeaways are shown here. I'm showing you here the power savings with our approach versus the monolithic ASIC for all of the different algorithms that we wanted to look at. Now, I should also say that all of these things that we built were done using high-level synthesis tools. So we used whatever optimizations HLS tools give us to drive the hardware down to low power. But if you handcrafted the design, I'm sure you could push the power envelope down further. So there's more savings to be had with that approach, should one wish to go there. But our focus really was on first trying to support the entire palette of algorithms that we were interested in. And so the design principles that went behind building up Halo have sort of gone over as I've summarized this, design overall. One thing that I haven't really talked about a bit and is worth mentioning is what I've really done is argued for the design of many accelerators that are distributed in some sense. In particular, what I mean by distributed is that the real benefits of this approach arise from the fact that every single accelerator is operating in a truly distinct clock domain. Normally, when you buy an SoC and you see different frequencies that different modules operate at, they're not really in distinct clock domains. They're operating off a central rail in steps or multiples of it. Here, we are in really different clock domains. And so you have to be careful when you are dealing with that you don't run into synchronization issues as you move data between, as you do inter-clock domain crossings. There are FIFOs that we have to design that deal with the fact that tokens are generated perhaps at different rates by upstream accelerators than the rate at which they're sunk on a downstream accelerator. These are well-known methods. There are well-known sort of VLSI methods to do this right. We've been working with Rajat Manohar at Yale to do this correctly, but I think the bigger point I'm saying here is the trade-off is, yes, we can drive power down, but there is a question, I think, of how many truly distinct clock domains can we scale Halo up to? And so that is a question that we're trying to answer. And I'm going to show you, and we're trying to do it with tape outs, which I'll talk about in a second. But that is the central trade-off over here. Okay, so with Halo, what is the current status? I presented to you that we've got these collection of ASICs. I haven't talked to you about this yet, but we also actually have embedded RISC-V microcontrollers on the system. And we have it because you need something to configure those programmable switches and to also sort of embed any firmware for other kind of system maintenance and telemetry that we haven't talked about. So we have microcontrollers to do that. Going forward, we're interested in building hardware that sits sort of in between microcontrollers and ASICs in terms of performance per watt and programmability. And so we'll be looking at vector processors, CGRAs, and FPGAs to do this. And one of the reasons, as I mentioned at the start of my talk, is I'm looking for postdocs in particular, is that we have NIH funding to kind of pursue this topic. So if you're interested, please reach out. Okay, microcontroller-wise, we have these two-stage 32-bit in-order RISC-V microcontrollers. The left side shows you a snapshot of the chip diagram overall. We're building the chip up incrementally, so we haven't taped out everything all at once. The PEs that are shown in black on the right, that's what we've actually taped out so far, and we'll be sort of doing more in the upcoming years, in the next, I'd say, year or so. So how do we fare in terms of power? These are some numbers that capture that. These are all the various components of the implant that I'd shown you before. The red line over there, which is 12 milliwatts, shows you the cap that we don't want to exceed. And I'm showing you here the radios, power going on the radios, the accelerators, which is in the portions in blue and the portions I've shaded, but also power that's dissipated by the sensors when you electrically stimulate the brain, and on what I call control, which is the micro controller actually programming up the switches. And so as you can see, the blue portions, I mean, power is really distributed everywhere. And so right now the interconnect, which is in yellow, isn't really taking up the bulk of power, although for the movement intent and seizure prediction, you can see it's a bit higher. So we sort of do have to attack this. In other words, power here is really a death by 1,000 cuts kind of problem. So no one component should be targeted. You really have to co-design everything on the implant is really the takeaway here. So the big next steps, we're looking at doing a V2 of our tape out in the next year and animal testing it for epilepsy treatment in particular. Um, with epilepsy treatment, there's a couple of options that we're interested in for human use eventually. There's a company called Longevity, which we're interested in working with, that designs cranial prosthetics that might allow us to kind of get a little more power headroom to play with. Basically, a cranial prosthetic is something that you can take off a portion of the skull and get this sort of biocompatible material that gets hermetically fused with with the skull tissue, and you can embed electronics on this. And so this is something we're kind of interested in exploring going forward. So overall, this is what Halo offers. And remember, though, that Halo is single site interfacing. So I'm going to talk to you very briefly about how we've been doing multi-site interfacing beyond that. But before I go there, I just want to point out there's many open research questions here to look at. We designed our accelerators in a very manual way, but there should be automated program synthesis driven ways that could be interesting to look at here. CGRAs, vector processors. It's an open question how to support machine learning techniques on the implant. There's also a lot of connections with AR, VR, XR that I'm interested in exploring. So many, many open questions to kind of look at. But what I want to briefly do now is talk to you a little bit about the multi-site interfacing stuff that we've been looking at and sort of end over there. Okay, so very, very briefly, why are we interested in multi-site interfacing? Again, it's because many neurological disorders are these network level disorders. So if you have something like epilepsy, a seizure often starts in one location and propagates to another. And so if you do have implants placed on different brain regions, one of the nice things that you can do is if you detect a seizure in one brain location, you can exchange information with other implants to work out whether there's correlated activity on the other end, and then electrically stimulate any target regions where you think the seizure will occur, and that'll improve your treatment options. Okay. Now, compute and communication are not the only challenges coming in the way of this distributed BCI design. There's many issues to sort of confront with surgically inserting multiple implants, packaging, compute and communication, so on. We're focusing on the compute and communication side. And one thing you might think is, well, do these implants get thermally coupled with each other? In other words, I made a big deal about this 15 milliwatt power budget. If I have more of these, is that a problem? Turns out actually that you have cerebrospinal fluid in your brain that allows you to dissipate the heat. So as long as the implants are spaced about 20 millimeters away from each other, they won't thermally couple. So that is good news. What is not good news is that to do the kind of correlation studies I was discussing, you have to send a ton of data between the implants. So much data, in fact, using the radios that you can have for inter-implant communication, that just transmitting the data is going to violate your 10 millisecond window that you get to respond to a seizure. And so we've done a lot of work to kind of deal with this. The basic idea that we've looked at is using algorithmic techniques like locality sensitive hashing to cut down the communication overhead. The basic idea is that these two signals here may look they look similar, but maybe squeezed up. You can detect that they are similar using locality sensitive hashes. And then the setup would look something like this. You have a source implant. It's pulling in signals from the brain, but it's also generating these locality sensitive hashes. It relays these much shorter locality sensitive hashes over to the other implants, which check for a collision with their own hashes. If they detect a collision, they tell the source implant, okay, I think it's now likely that you do have correlated data. Stream the data out now completely so that I can test for that. And if I do have correlated data, which I can test using a bunch of similarity measures that I'm showing you over here, then I now know that I have a correlated seizure. So we built hardware to accommodate this kind of correlation checks. I won't get into that in excessive detail. And our design uses familiar software abstractions. You can program all this stuff in MATLAB and so on. And there's a ton of data that I have that shows that even though you can have false negatives and false positives with these types of signal detection correlations, they don't really lead to a degraded form of seizure treatment. In fact, what happens in the worst case scenario is that you perhaps delay the electrical stimulation that you're supposed to do for seizure treatment. But for the kinds of data rates that we see, you will delay by sub, like in sort of the microsecond scale. So it's not really going to impact the quality of the treatment excessively. Okay, so I am at the 50-minute mark now. And this covers the vast majority of what I wanted to get through in terms of the data and the motivation for the work. So I'd like to stop now and take any questions that you might have on the work that I've just presented. Thanks for listening.